Hello everyone. I'm Dr. Anand Kumar from Department of Information Technology, NITK Surathkal, Mangalore. So here I'm going to give a short introduction about sequence modeling and recurrent neural network as a part of deep learning lecture. This is the outline of the presentation. So the motivation of RNN and sequence modeling, or we'll see what is mainly sequence modeling, and we'll see the unfolding computational graph, how we are reaching that RNN model. What is the mathematical background of RNN, and we'll see some of the RNN variants and BPTT and bidirectional RNN encoder decoder architecture. Before going to the motivation, so RNN is a part of network architecture, comes under deep learning models. So deep learning, if you see, widely applied to most of the domains. Particularly here, we are going to talk about natural language processing using deep learning. How to solve the natural language processing problems using deep learning. Here, I have taken the networks called recurrent neural networks to handle the sequential data. The motivation of this is, if you see that, the motivation of this lecture is to introduce RNN. So recurrent neural networks are a family of neural networks. So it comes under the neural network family. So they're mainly used for handling the sequential data. So what is mean by sequential data? So the main question. So before choosing any neural network architecture, any deep neural architecture, so we should know that, so what kind of data and what kind of application is suitable to that architecture. That is very important. So we should not blindly apply the neural network architectures to the data set or to any application. And we should not follow the crowd also. So most of the people are applying, so I'm applying. So that is not a right way to do that. We should have a reasoning for applying any neural network architectures to a particular problem or to a particular data set. Here, if you see that is the reason why we are saying that recurrent neural networks are very good in handling sequential data. Before that, let me say something about sequential data. When you say sequential data, so we can divide the sequential data into two types. So one is data as a sequential data. So one is data changes over the period of time. Any data changes with respect to time, and we can say that it comes under sequential data. The example is time series data. All time series data, you can say it's a sequential data. So stock market prediction, cryptocurrency values, gold price, petrol price, temperature value, all we can say that it varies over a period of time. COVID cases varies over a period of time. So all you can say it's a sequential data. So the other part of the sequential data, if you see that, so you can say one is you can say it's NLP data or sequence data, not only the NLP data, the other sequence data. So one data is the data changes over a period of time. Other one is a sequence data. When you say sequence data, not only the NLP data, other data sets are also there. Say for example, a protein sequence, any bioinformatics sequence, drug sequence. So these are called sequence data. Here we are going to talk about NLP data. So NLP is also a sequential data. Say for example, the first line of this slide, first point of this slide, recurrent neural networks or RNN or a family of neural networks for processing sequential data, that is called a sequence. Why we are calling this as a sequence? The reason is it follows some order. So we are keeping the words, we are putting the words in particular order. If I say that recurrent neural networks, if I say in that particular order, then only the meaning is conveyed properly. Instead of saying recurrent neural networks, if I say that networks neural recurrent, so there is no meaning in that. So all the NLP data is considered as a sequential data. If you take NLP huge corpus or a sentence, you can say it's or a paragraph, anything can be a sequential data. Another important thing in NLP data is not only the words, not only the set of words are forming the NLP data, sorry, sequential data. Say for example, word 1, word 2. So what we are expecting is this word should be in a particular order to convey this expected meaning. Not only the words are forming, even the characters are forming. If you see here, this word closely, processing, it consists of characters P, R, O, C, E, E, S, S, I, N, G. If I spell or if I write in this following order, then only the exact meaning will be there. If I write something like S, I, N, G, S, E, P, R, O, something like that, this is completely different from processing, but maybe the same spelling or maybe the, so here, not only the characters, the order is important. In NLP data, the sequence information, the sequence is there in the words as well as sentence. If you are thinking about the big corpus, particularly a big stories, definitely the NLP information, the sequence information is there in a paragraphs or sentences also. This is called a sequential data. So before RNN, before recurrent neural network, like recurrent neural network, so one more popular algorithm in deep learning is convolution neural network. So we'll see that how that convolution neural network is differ from recurrent neural network. When you say convolution neural network, it's usually applied to the computer vision problem, or we can say the data is in a grid. If a data is in a structure of grid, then you can apply convolution neural network. A grid means a data is in the form of a matrix, or we can say a tensor. It's a 2D grid. So that's the reason we are saying that computer vision is for computer vision applications, we are applying convolution neural network. This is this is a 2D grid data. If you say about sequential data, so data will be like this. So data will be in certain order. Say for example, NLP, so this will be W1 and this is a W2, word 2. So like that, this will be a WN. So sequence or order. So the order of words, you can say it's a sentence. The next important thing, the motivation. So why we are going to the recurrent neural network? Recurrent neural networks are very good in processing the sequences of variable length. So the architecture is like that. It handles a variable length sequence. Say for example, the same slide I have taken, the same slide, we have 3 points in the slide, 3 NLP sentences are there. If you take the first one, we have 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9 words are there. So 9 words form this sentence. Here, the next one may be 13. So, okay, say for example, I'll say that 13 words are there. The next one maybe 15 words are there. You can see this is the best example of variable length sequence. So RNN are good in handling the variable length sequence. We cannot expect the model to give a same length sequence because it's a sequence, right? Particularly in NLP, so most of the sequences will be in variable length. Another important concept of RNN is parameter sharing. So where we have the parameter sharing concepts in CNN also. So the parameter sharing, when we just see the architecture, that time the parameter sharing part will be very clear to you that. So it shares the parameters. Parameters here I can say that weight and bias. It shares the weight and bias between the nodes or between the units. So I'll explain that parameter sharing concept when I explain the architecture, so that time it will be very clear. Now, the difference between the convolution and RNN. So when you say convolution, so the convolution, as I said that it's very good. The convolution network are very opt model for handling grid data, or you can say images. Now RNN, it's very good at handling the sequence, capturing the information from the sequence. If you say that convolution, the output of the convolution, if you see that it's a member of the output, the output of the convolution is a function of small number of neighboring members. When you say convolution, if you say that this is the actual image and this is our convolving filter, so usually we try to take the information from the filters like this. So I'm calling it as a small number of neighboring members. But in case of RNN, so we have a sequence. We have a sequence word 1, word 2, word 3, word 4, word 5, word 6. Here, the output is a function of previous members of the output. So this word is depending on the previous word. This word is depending on previous word. So that means that then only we can form it as an order, right? So this association we are capturing. So RNN, how the RNN is differ from CNN. So once again I repeat that. So the CNN is the output of the CNN is a function of small number of neighboring members. Here it's a previous members. So previous members. Okay, this I'll just skip this one computational graph. I'll directly go to that RNN. Yeah, this is an example of RNN network. So when we say that RNN, so the architecture is look like this. Here X is an input and O is an output and S is a hidden layer. So this is an unfolded representation. So this is a fold. So this is a folded representation of RNN. This is the unfolded representation of RNN. When it comes from the folded representation, if you see that there is an input and there is a hidden layer, there is an output. It's similar to the feed forward network, but the difference is we have a feedback connection. So in feed forward network, we don't have a feedback connection. Here we have a recurrent connection. So the recurrent occurring in hidden layer. So input, output, input, hidden layer, output. And we have something called recurrent connections. So this is a recurrent connection. I'll take a pointer and then I'll explain it. Okay, here if you say that this S I'm saying it's a hidden and X is the input, O is output. So when if we closely see that X we are converting to S, from S we are getting O. So when you are mapping or when you are transforming this X to S, so we are doing the linear transformation. So we are having the weight U. So this helps to transform X to S. So here I'm not considering the bias. So if you see that I'm doing a kind of mapping, my S is a vector. If you see the S equal to the linear transformation. So the linear transformation here gives by the matrix U, weight matrix U into dot product X. Or you can call this as a U transpose X also. So this is a weight. This is a weight we are going to learn. Initially, the weight will be assigned randomly. So once the model trained with the real-time data, so we'll learn the optimum weight. So this is a one weight matrix U, S and X. So linear transformation. We got X, S. From S, we have a recurrent connection, right? So it means that the recurrent connection T plus 1. Each timestamp we are here. So T plus 1, S of T plus 1 equal to. So W into ST. Here W is the linear transformation, or you can say W transpose also. This is a weight, second weight. Next step, output O. So in order to get output O, so O equal to, we have a linear transformation B. So B matrix, I'll say transpose, and I can say S T plus 1. Sometime in some reference, they used to have ST, but the actual one is ST plus 1. This is how we are taking an input X and we are converting into output O. So we have a three learnable weights, three learning parameters. So when you say learnable parameters except bias, I haven't considered the bias here, U, V and W. U is for mapping input to hidden and W is for mapping hidden to hidden and V is to from mapping from hidden to output. If I unfold this architecture, so I'll get them each timestamp. I'll get like this: t minus 1, st minus 1, ot minus 1, xt, st, ot. So we have seen something called parameter sharing. Hope you remember I said about the parameter sharing is an important concept. So because of the parameter sharing only, people are moving to the CNN and RNN. So the parameter sharing reduce the number of parameters and reduce the computation when compared with the feed-forward network or deep neural net, or multi-layer perceptrons. If you see here, xt minus 1 and xt minus 1 is each timestamp I have. Say for example, if you have a sentence, it's a recurrent neural network. This is a recurrent, this is a neural, this is a network. So the parameter sharing concept, as I said that here, we are using the u as a parameter. The parameter u is not only used for the first value or the first unit of your sequence or first word of your sequence. You can see here, the same u is used everywhere. So we are considering the complete sequence as a single output and we are learning the u. So the u is going to be same. The size and the values of the u going to be same. If you are assigning the value random, initially you are doing the random initialization. So that whatever value assigned for u, the same value will be here and same value will be here. So the this is the linear transformation. As we have seen that xt minus 1 is converting to st minus 1. So like that, the parameter sharing is happening in W also. W is between the recurrent connections. And V is from hidden to output. The same architecture, the same neural net architecture drawn here. If you see that, it's unfolded things. The input we have, and we have a hidden complete unit, hidden unit, or an unit. We can call it as a hidden unit, and we have a H0, H1, H2, H2. So this is a simple introduction of recurrent neural network. So with this, I'll stop now. So the next session we'll see about how we can form how we can come up with the equations of recurrent neural network and the different variants of recurrent neural network. Thank you.